All right, hello everyone. Welcome to my talk on blast radios. As you can see, I renamed it to Breaking Enterprise Network Authentication because I couldn't fit the entire title on a slide. But jokes aside, this is joint work with Sharon Goldberg, Nadia Henninger, Mike Milano, Dan Shumoff, Mark Stevens, and Adam Sewell. And as you can tell from the latex slides, I'm a cryptographer, so I will bring you equations instead of source code screenshots. But before you all run out of the door, I can promise you I'll keep things understandable and that you will learn something new in this talk. So let's start with what is radius and why should you care about it? Even though you might not have heard of radius yourself, your infrastructure most likely does depend on it. Radius is often hidden from the end user, but it is the de facto standard authentication protocol in enterprise networks. And so with that, basically every network equipment that was produced in the last 25 years is supporting radius. And so that means radius is used, for example, to authenticate administrator access to internet backbone routers. Essentially, every non-cable ISP is using radius for authentication and accounting. Radius is also used to authenticate access to power grid equipment as well as industrial control systems. Radius is also used as a backend in identity providers such as Okta and Duo, and it's also used in 802.1x and therefore to connect users to enterprise Wi-Fi and Eduroam. In this slide, I tried to compress our entire attack onto one slide, so in case you want to check your emails later, this is the slide you need to pay attention to. Let's start with what is radius. Let's consider a user that wants to authenticate to a router. For doing that, the user sends their username and password to the router. But in most enterprise networks, the router itself doesn't actually store the user credentials to check whether that user is allowed to have access or not. Instead, you have one centralized authentication database, and all the other devices connect and contact that database and then ask whether the user should be granted access or not. And that's exactly what radius is used for. So the router, acting as the radius client, will contact the radius server and send an access request radius message to the server asking whether it should give this user access or not. And this request has attributes attached to it that include the username and password. And then the radius server will look up these user credentials in its database and communicate its access decision in the form of an access accept or access reject radius message that is sent back to the radius client. And based on this message, the radius client will then decide to give the user access or not. Most of this radius traffic between the radius client and the radius server is actually sent over UDP. And I know this is hard to believe, but actually radius over TLS is not even standardized yet. So really, in practice, a lot of this traffic is still sent over UDP. Blast radius is a protocol vulnerability that allows a machine in the middle to change an access reject to an access accept. And that means that the adversary can authenticate as any user. So for example, if you are using radius to authenticate administrator access to an internet backbone router, then that means the adversary can authenticate as the administrator on that device. Our attack also helped accelerating the ongoing efforts to deprecate radius over UDP, which are still ongoing in IETF. We disclosed our attack to over 90 vendors, which included all big producers of network equipment such as Cisco and Microsoft. So I hope with this I piqued your interest in blast radius, and maybe you're wondering, am I vulnerable? How does this attack work? Or shoot, I'm running radius, how can I mitigate this? Well, if that's the case, then maybe don't open your mailbox, because I will answer all of those questions in this talk. Let's start with the radius protocol. The following 3 packet formats are important for our attack. In radius, every packet starts with a 4-byte header that specifies the packet type and length. In the access request, we then have a 16-byte request nonce that ensures the freshness of answers. In addition, there can be a number of attributes attached to an access request. The most important ones of those are the one that holds the username and a scrambled password. The access accept, which is one of the answers that the radius server can send back, has a similar structure. It also has a header, but it now has a response authenticator instead of the request nonce. And this should prevent an adversary from forging responses of the server. It can also have attributes. These attributes can include, for example, what kind of privileges the user that is authenticated should be granted. Access reject has a very similar format than access accept. It also has an authenticator, but it usually has less attributes. And as you can probably guess, this attack is focusing on the response authenticator. So let's see how this is constructed. As the name suggests, the response authenticator should prevent an adversary from forging answers of the Radius server. And this is done as follows. To compute the response authenticator of a response packet such as the following, the server computes the MD5 hash over the response header and attributes, which are copied from the response, as well as the request nonce, which is copied from the request, which is the access request that this is a response to. And finally, also a fixed pre-configured shared secret. So this shared secret is set up when you set up this authentication system. It is hard-coded in both the Radius client and the Radius server. And this is also what should make it hard for an adversary to forge this response authenticator, because the network adversary doesn't know this shared secret. All right, so I'm sure a lot of you are already shaking your heads that Radius is still using MD5 in 2024. After all, we know that MD5 has weaknesses since before I was born. And that's exactly how our research started. Sharon Goldberg, one of my co-authors, noticed how to implement Radius for a customer of her startup, and she noticed that it's still using MD5. And so she called my advisor, Nadia Henninger, and told her that she should break Radius. And Nadia was very much on board of this, and so I, as her student, and the other collaborators entered the project that way. But at this point, I would like to emphasize that it's by far not trivial to break Radius just with MD5 collisions. In fact, the IETF working group that was designing Radius was aware that MD5 is broken. However, they thought that it is a testament to the design of Radius that there have been, as yet, no attacks on the Radius authentication signature. So in other words, they thought that because no one could figure out how to use MD5 collisions to break Radius, that Radius is secure. In the next section of this talk, I will explain how to use MD5 collisions to break Radius. Recall that the goal of our attack is to forge an access accept without actually knowing the shared secret. And so that means we need to get around this response authenticator. This is where the MD5 collisions come in. We will carefully craft a collision such that an access accept and an access reject response both have exactly the same response authenticator. So here is the first equation of my talk. Not that bad, right? All right. So the attack works as follows. The attacker logs in with a username and some random password that is definitely wrong. This will trigger an authentication, an access request that is intercepted by the machine in the middle. So this is the second part of the adversary. And this, the adversary then uses the information in the request to predict what reject the server is going to send. And then it will run an MD5 collision to find the matching accept that has the exact same response authenticator. However, at this point in the attack, we don't yet know what this response authenticator is. And so the attacker is modifying the request to make sure that the Radius server will respond with exactly the reject that it predicted. And at that point, it can read off the response authenticator from that reject, and by construction is the same as the one for the accept. So the adversary can just copy over this response authenticator to the access accept, and this will trick the Radius client into granting the attacker access to the router, although the attacker didn't know the correct password for that user. So in order to understand how this works on a technical level, we need to first revisit MD5 collisions. The first collision, or the first weaknesses in MD5 were found in 1993, but it took until 2004 to find full MD5 collisions. And so that means A full collision is an unstruct that we find two unstructured strings of bytes, which we call gibberish, G1 and G2, such that the MD5 hash of G1 equals the MD5 hash of G2. Now, these collisions can be computed in seconds on a laptop, but they're not very useful for an attacker. The reason for this is that an adversary needs more control over the collision. And so an improvement over these collision attacks are so-called chosen prefix collisions, where the adversary can choose two prefixes, P1 and P2, and can then run the collision algorithm to produce gibberish G1 and G2, such that the MD5 hash of the prefix P1 concatenated with the gibberish G1 is the same as the MD5 hash of P2 G2. And this was used in 2009 to create a rogue TLS-CA certificate. We're actually using an extension of this attack where once you have a collision, the structure of MD5 guarantees that you will still have a collision even if you append the same suffix to both inputs of the MD5. And this will be very useful for our attack. In the last 14 years, there wasn't really a lot of cryptanalysis with MD5, and also protocols avoided using it until our attack on Blast Radius. So let's see how we can use this MD5 chosen prefix collision attacks to break Radius. Here recall that our goal is to create an MD5 collision such that a forged access accept has exactly the same response authenticator as the predicted access reject that the server sends. This is done as follows. The adversary sets the header, request nonce, and attributes of both the accept and reject as the prefixes for the chosen prefix collision attack. And then it will run the chosen prefix collision attack to get some gibberish, one for the accept and one for the reject. And so at this point, the prefixes plus gibberish produce the same MD5 hash. And as we've seen before, once you have a collision, you still have a collision if you append a random, the same string to both inputs. And that's very useful for our attacker because the attacker doesn't know which secret is appended, but it knows that the same secret is appended to both of those packets. And so therefore, we still have a collision, even though the adversary doesn't know the secret. Now at this level, this looks a bit more simple than it actually is. And so next I will discuss 3 subtle challenges when you run this attack. The first challenge is that the adversary must convince the server to actually include this reject gibberish in its response authenticator computation for the access reject. And so this seems a little bit impossible at first, because why should the server include some random bytes that the adversary would like it to include in its answer? But it turns out that there is an attribute that is perfect for running this attack. It's called the proxy state attribute, and the standard mandates that the server must include this attribute without any modifications in the response. So that means if we have an access request with a proxy state attribute, then the server, if it follows the standard, must copy this attribute onto the access request, access reject. And so the goal here is that we can hide the reject gibberish in such a proxy state attribute. But there we run into a second problem, which is that hiding the reject gibberish in a single proxy state attribute is actually too slow, because it would require us to create a very short reject gibberish string, which is expensive to do with chosen prefix collision attacks. And so the idea to get around this is that we spread the gibberish across multiple proxy states. And so for this, we had to modify existing chosen prefix collision attacks such that they allow us to put a 4-byte proxy state header into the middle of the gibberish. So you can see here that our gibberish string is actually parsed as 2 different proxy state attributes. Note that the first proxy state header we actually don't need to put into the gibberish. We can hide this one in the prefix, and that makes computations faster. The last challenge that I will talk about is that you can note that in the prefix, we need to know the request nonce. And so that means that the adversary cannot pre-compute an MD5 collision. It needs to wait until it sees the access request before it can compute the collision online. And that's an issue because the Radius client can time out while it waits for an answer from the Radius server. And so that's particularly bad because those chosen prefix collision attacks are pretty slow. For example, to compute the rogue TLS-CA certificate, they ran the attack for 28 hours on a cluster of 215 PS3 machines. And indeed, our attack first took multiple days, but we were able to optimize the time down to below 5 minutes using both algorithmic improvements as well as parallelization. So let me say a few more words about what we did. Here is a screenshot from our monitoring. This was somewhere in the middle of our optimization process. So you can see here that collisions still took about 30 minutes at this point. But the monitoring shows nicely the different phases of the algorithm. But first, one thing that's not shown in this picture is that we moved a lot of the computation into pre-computation that's independent of the prefixes. And so that way we can also save some time. But what you see in the screenshot is that in the first third, we run this part of the attack on the only machine that we had access to that has GPUs, because that part of the attack, it's called the birthday search, is much faster on GPUs. Later on, we found a way to use both GPUs and CPU machines, and that way we were able to get down this part below 1 minute. And then you see in the remainder of the image that we sort of have alternating phases of sequential computation and parallel computation. And so the way we were able to parallelize that part of the MD5 collisions is that we noted that those are probabilistic code paths. And so we run many of those, the same computation with different random seeds on all of the machines, and then we take the one that finishes first. And so to actually gain runtime improvements from this, we also tuned the parameters to favor runtime over success rate. So many of those executions that run in parallel will fail, but the ones that finish faster than before, and this way we get an overall runtime reduction. Here is an example with bits and bytes of two correctly formatted access accept and access reject packets that have the same MD5 hash. I had to concatenate them to fit them on the slide, but this example is also available on our website, together with some code to compute the response authenticator. So if you want to play around with MD5 collisions, you are very welcome to check out this Python code. But let's move on to impact. Our attack affects both pop, chop, and MS chop modes for radius. It doesn't necessarily affect the eat modes of radius. This case is a bit complicated, and so I have a separate slide for this later. Our attack also requires machine in the middle network access. And so that means if you send your radius over UDP traffic over the open internet, you're definitely vulnerable. You might wonder, why would anyone send this traffic over the open internet? And is anyone doing that? Well, the answer is actually a surprising number of people are doing this. This includes cloud providers and telecommunication networks. The other way to run radius is to run this traffic inside a VLAN or inside an IPsec tunnel. And so in that case, our attack can be useful for lateral movement, meaning that once the adversary compromised that network, it could use blast radius to gain access to all of the devices that are on this network that are using radius for authentication. In terms of timings, most radius clients that are used in practice have timings configured of up to 60 seconds if there is multi-factor authentication involved. Our proof of concepts take about 5 minutes, so that's a bit longer than the timeouts that are used in practice. But really, this should be taken as a very generous upper bound because we're an academic team and we don't have that many resources. In fact, you could have more computational resources than we have by spending $50 on AWS. And moreover, there's also many more optimizations that would be feasible. Our attack parallelizes well, and the MD5 collisions could even be implemented on hardware. In terms of proof of concepts, attacks that we ran the blast radius attack against the following software. And in all of these cases, it would allow an attacker to authenticate as an arbitrary user. So first, we tested FreeRadius, which is the most widely used radius server. We also looked at Okta, which is an identity provider, and found that they are vulnerable if they are configured to use radius in pop mode for multi-factor authentication. We also tested our attack against the Cisco firewall that can be configured to use Radius to give users access to the serial console, or to put them on a VPN, or for many other network services. On the image you see on the right side, there is our firewall that is connected to the laptop in the middle, which uses a very hacky UDP over DCP TCP tunnel into our cluster, where we run our machine in the middle software that will then forward the packets to the actual Radius server and run the MD5 collisions. And you can also configure pluggable authentication modules on Linux to use Radius, for example, for users to log into a machine via SSH or to run sudo. And in all of these cases, we confirmed that none of these deployments are using a message authenticator, which is something that would prevent our attack. And also, we made sure that the clients accept packets that have proxy state attributes, which is something that is sort of unexpected in a normal use of the protocol, but we need those proxy states to hide our gibberish. And none of these complained about this. So I promise you an extra slide on EAP. EAP is a bit complicated because the EAP TLS mode for Radius doesn't actually do what you would expect it to do. It doesn't protect the Radius packets. Instead, it's EAP TLS nested inside a Radius communication. And so this is not to be confused with Radius over TLS, which actually wraps the entire Radius communication inside the TLS channel. So going back to EAP TLS, the way this works is that the Radius messages have an EAP message attribute, which then has the encapsulated EAP messages. And so the standard requires that if you have an EAP message attribute, then you also need to have a message authenticator attribute. And I said before that this attribute prevents our attack. So this is looking good for EAP at this point. Unfortunately, the standard is very unclear as to what should happen if an access accept doesn't have an EAP message attribute. And so one possible attack that could work against some clients is that an attacker strips away both the EAP message and the message authenticator. But at that point, you run into another issue, which is that the higher level protocol, such as Eduroam or 802.1x, might negotiate a key inside the EAP session that is nested inside the Radius traffic. And so even if you can forge an access accept that the client validates on the client, the adversary doesn't actually get this EAP key, the key that is negotiated inside the EAP session. And so that means exploitation in practice is really tricky. But let's move on to mitigation in general. We disclosed this attack to over 90 vendors in a big disclosure that was coordinated by CERT. And the challenging thing about mitigating this attack is that there are many different use cases for Radius. For example, it's even used to authenticate access to windmills in power plants. And the problem with that is that some of these applications are really hard to upgrade. And that makes backwards compatibility a major requirement for mitigations. But in a collaboration with the vendors, we developed the following mitigations. In the short term, we recommend that implementations use the message authenticator attribute, which uses HMAC MD5. And despite that there is also an MD5 there, that is actually not vulnerable to the MD5 collisions that we found in our paper. This mitigation only works, though, if all of the requests and responses actually include a message authenticator and also verify it. On the long term, we recommend that all of the Radius traffic is encapsulated inside TLS, which is the more robust solution. And there is actually a current draft that the IETF is working on standardizing for Radius over TLS, so keep an eye out for that. So now that it's about 6 months after we went public with this vulnerability, we can make sort of a review and see how is mitigation going. Of course, all of the Radius server software providers had patches available at the time we went public because of the responsible disclosure. But it looks like until now, also all the equipment or many of their equipment vendors have upgraded their systems. However, there seems to be some misunderstandings about the placement of message authenticator of the message authenticator attribute. So for example, Juniper devices fail if the message authenticator is not the first attribute. And Cisco devices put the message authenticator at an arbitrary location. And so you can clearly see that those two are incompatible. And so if you have a Juniper and a Cisco device in the same network, you have a problem. We think that the source of confusion for this is the message authenticator hiding attack that we outline in our paper. And so this is basically works as follows. If the message authenticator is not the first attribute, the attacker can effectively remove the message authenticator. And it does this by making sure that the accept gibberish ends in a proxy state header. And so if you do that, then the client will parse the message authenticator as a proxy state instead of a message authenticator attribute. And so it will not actually authenticate the packet with that value. So going back to the question of where should you put the message authenticator, if you are sending a radius packet, you should definitely put it as the first attribute because that avoids the previous hiding attack. However, if you are receiving a radius packet, then you should not mandate that it is the first attribute. And the reason for this is that it first of all violates the standard and it also breaks backwards compatibility. If you do this, then deployments that always require the message authenticator are actually still not vulnerable, even though you don't mandate the order. And the reason for this is that the adversary cannot create new message authenticators. It can only remove one that is there. So if you always require the message authenticator to be present, then you are still secure. However, of course, if you don't require the message authenticator to be there, then depending on where it is placed, you might still have some vulnerable devices. This was it from me. If you want to learn more, there is our paper that was published at Usenix this year. We also have a website that you can visit, and I'm very happy to answer questions right now or on the hallway later. Thank you very much for your attention. Yes, please.
That you had to increase the time in order to get to work outside of what would be considered standard. Given that anyone can spin up an AWS cluster for quite cheap, what sort of time span are you looking at for the more common standard deployment for the timeout management? How much do I have to scale up my compute resources, basically?
Okay, that's a great question. Let me repeat it for everyone. The question was, how much would you need to scale up the computation to run attacks against real-world deployments of Radius? So the timeouts that you have in practice are between 15 seconds and 60 seconds. You have longer timeouts if you need multi-factor authentication because people need to have time to, click the second factor authentication message. So you would need to have a speed up between 5x and 20x compared to what we had. I think a lot of it you could do by spending more time engineering and rewriting Hashclash to be more optimized for example, caches and so on. So you could do a lot of it with engineering efforts. I think if you would do the brute force approach of just scaling up your computational resources, I would expect that you would need more than the 5 or 20x time because not everything parallelizes as well. There are the sequential parts in the computation that don't parallelize as well. However, if you have stronger GPUs, which we definitely had very cheap GPUs, then you could get at least the first phase probably down quite a lot. So yeah, it depends. It's probably the overall answer. Yes, please. Yes. Yeah, okay, so the question was, I mentioned multiple times that Radius is run over UDP and it's unclear how running it over TCP would fix it. That is correct. if I mentioned running over TCP would fix it, then I misspoke. It's definitely the case that you run it over TLS to fix it, meaning that you actually encapsulate the radius traffic inside TLS, and it will still have its weird MD5 construction, but it will no longer be insecure because you rely on TLS to provide the integrity and confidentiality that radius doesn't provide. So yeah, over TCP does not fix it. But that is, yeah, the standard is over UDP, and the other standard is over TLS. Yes, please.
Have you seen any evidence in a while for using them?
Great question. The question is whether we've seen any evidence that this has been exploited in the wild. This is a great question, and we don't have the insight into figuring this out. I think if companies have logs of the access reject messages or accept messages that were sent, they could, in hindsight, find out whether this attack was run or not on their infrastructure. We have not heard back of anyone that this has been exploited in the wild, but it would be detectable. But I suspect that they might not keep this log because it's sort of, you need to log the entire raw packet to figure this out, and not only sort of some metadata. So no, we don't know if anyone has exploited this. But if any one of you knows, I would love to hear about this. It looks like we're out of question. Thank you very much for your attention, and enjoy the rest of the conference.